recall that our kinematic equations for linear motion and angular momentum are very similar. So we would have delta D equals V naught T plus 1/2 the acceleration times time squared. The rotational analog of this would be delta theta, which is our change in position on a circle. It's equal to the angular velocity times time plus 1/2 the angular acceleration times time squared. Likewise, we have the final velocity is equal to the acceleration times how long it was accelerating for, plus whatever our initial velocity was. The angular equivalent is omega f is equal to alpha t plus omega naught. Keep in mind that these two pairs of equations are vector equations, so direction matters. In the linear example, up, down, left, right, north, south, for example, it's very straightforward to figure out the direction. For rotational mechanics, it is important to remember the right-hand rules. Is it into the page or out of the page? This is a way of uniformly agreeing on the rotation, because clockwise and counterclockwise will be dependent on your point of reference. The third of the kinematic equations is the one that only deals with scalar properties. It is not a vector equation. And that's the one that has Vf squared is equal to V naught squared plus 2 times the acceleration times the change in position. For angles, that means it's omega f squared is equal to omega naught squared plus 2 alpha delta theta. Both of these do not require us to figure out the direction because it's only dealing with the magnitudes. Mathematically, this is because the squaring, we actually lose the information of the direction with the vectors. Keep in mind, there's another equation, the centripetal acceleration, which is what caused us to turn in the first place. And if we're going about a circle, we will have centripetal acceleration, even if our tangential or linear velocity is constant. So this is what's giving us the direction change, and it's v squared over r. Keep in mind it goes towards the center of the turn, and it is a linear acceleration, not to be confused with the angular acceleration, alpha. If we have a bicycle tire and we allow it to spin for 1 revolution, we know that it'll roll forward a distance that is equal to 1 circumference. This is true because we're not allowing it to slip. So as long as there's no slippage, it will roll forward equal to the arc length that it rolled through. If you really want to figure out the direction, you have to use the right-hand rule. So here, from our perspective, it is moving in a clockwise manner. So if we curl the fingers of our right hand in the same direction as the arrow of rotation, our thumb will point into the page. So we use the into the page symbol to indicate the direction of delta theta. Our radius vector is always drawn from the point of rotation to the point of contact. So in this case, it is a downward radius. Maybe we don't know what direction a tire will roll because we've never seen one move. We can calculate this using what is called a cross product. It is a separate way of calculating the multiplication of two vectors. Earlier we saw the dot product when we talked about work, which was force times distance. That gave us a scalar. The cross product will give us a vector. Here we have to use the right-hand rule. This is a little complicated to draw on 2 dimensions, so bear with me. If you take your right hand and you point your finger in the direction of the radius vector, so in this case it will be downward. So you take your pointer finger, point it straight down. Now take your middle finger and point it in the direction that we found for the delta theta, which in this case was into the page. So radius is down, which is our pointer finger. Our middle finger points into the page. Now, this takes some twisting of your wrist. But you should find when you do these two, your thumb will point in a direction, which is in this case to the right, or a positive x direction. The vector equation we're actually solving is delta d is equal to the radius vector crossed with the change in angle vector, delta theta. So r cross delta theta. Now if we do our right hand correctly, we can figure out that it's rolling forward, which agrees with our common sense expectation. If the wheel were rolling the opposite direction, well then delta theta would be out of the page, and r across delta theta would give us a direction that is to the left, which is a negative direction. Fortunately, most of the time we only care about the magnitude. So delta d, the magnitude of the vector, or just its size, is going to be equal to the magnitude of the radius vector times the magnitude of the change in angle vector, delta theta. A lot of times you will see this just simply written as delta d equals r theta. So we don't have any direction information in this equation, but it is easier to calculate. For example, if this bicycle has a radius equal to 0.30 meters, 30 centimeter, which is not too crazy, and delta theta happen to be equal to 0.5 radians. It is important to keep this in radians, not degrees. So remember to convert. Well, we can figure out that that wheel rolled forward r delta theta worth, or 0.30 meters times 0.5 radians, which is equal to 0.15 meters. So the wheel rolled forward 15 centimeters. We know that delta d is equal to r cross delta theta. But what if this is changing in time? Now we're going to hold r as constant, so we're not going to have a changing r, so only delta theta can change. That means we'll have delta d over delta t is equal to r crossed with a delta theta over delta t. Well, delta d over delta t, well, that looks a lot to me like a velocity. So velocity is simply going to be the radius vector crossed with the angular velocity vector omega, which, if we wanted it in terms of magnitude, the speed is going to be equal to the radius of the wheel times how fast it's spinning, or the angular speed. Of course, we can also do the same trick and have a delta v over delta t. So a change in velocity over time is our acceleration. We're still going to keep r constant. So that means we're going to cross it with delta omega over t. Well, that means I have an acceleration vector is equal to the radius vector crossed with the angular acceleration vector. Once again, if we only care about the magnitudes, we don't have to worry about the cross product. Though, to warn you, there will be times when you have to worry about the direction. And it's worth remembering that if something is slowing down, the acceleration opposes the motion. So if it's spinning and slowing down its rate of spin, that means alpha is going to be opposite omega. Let's do an example problem. Let's say we have a spinning wheel. If the radius of this wheel happened to be 30 centimeters again, but we were told that the rotation rate, that it rotates at 900 RPMs. Well, our first step is to figure out what omega is. So what is omega? Well, it's how fast it's spinning, but RPMs is not the correct units. So we have to convert here. 900 RPMs So 1 rotation, or 1 revolution, is equal to 2 pi radians per 1 rotation times 1 minute equals 60 seconds. This allows us to cancel out the units we don't want in place of the ones we do want. You plug that in, you should get 94.2 radians per second. So here we have a problem. The wheel is slowing down from the 900 RPMs to 60 RPMs in the course of 15 seconds, and we need to figure out alpha. First, we must figure out what the new final velocity is, or omega f. We know that we had 60 RPMs, so we have to do a conversion. In this case, I'm going to do a little bit of shorthand, but it's 2 pi radians divided by 60 seconds. And this gives us 6.28 radians per second. All right, so now we can solve for alpha. Alpha is equal to omega f minus omega naught all over t. So 6.28 radians per second minus 94.2 radians per second, all divided by 15 seconds, gives us a negative 5.9 radians per second. Now, what does it mean to be negative? Well, keep in mind, using your right-hand rule, you curl your fingers in the direction of the rotation. Your thumb points into the page, which means that our omega naught is into the page. Now, it didn't completely turn around, so it just slowed down. Our omega f is also into the page, but it's slowing down. So what is a negative of the into the page vector? Well, it's an out of the page vector. So alpha is actually 5.9 radians per second squared out of the page. I will show more examples in the next video.